All right, let me talk about this handout, this chart that I've handed out here or given you a link to. What it has is a list of all the tests for converge or diverge. This is specifically a list about infinite sums from n equals 1 to infinity. So it's not about the actual limits or the integrals. It's just the infinite sums. So, for instance, on that first line, I call it the limit test for divergence. It doesn't have any requirements for application. It works on any a sub n. So, there's the test. You can take the limit as n goes to infinity. If it does not equal 0, that means that the summation of a sub n diverges. So notice the limit there is of the sequence. If the sequence limit doesn't go to 0, the summation diverges. If the limit of the sequence does go to 0, it's inconclusive, cannot conclude. And then the next one for another comparison, geometric series. So here's the requirements for application. The a sub n, the sequence, has to be r to the n. R is the real number there, and it has to be r to the n. So that is very specific. If you see a different sequence and you're asked what does the geometric series say, you would have to say it does not apply. But if it does apply, then you have the two possibilities. R is less than 1, absolute value of r, that is, less than 1, then the series converges to r over 1 minus r. If r is greater than or equal to 1, the series diverges. That one works both ways, so that it doesn't have any inconclusive. As long as it applies, it can't be inconclusive. You get converge or diverge. Same for p-series. Here, a sub n has to be equal to 1 over n to the p. That's the requirement for application. If it doesn't look like that, it doesn't apply. But then, if it does apply, you can check the p. If the p is greater than 1, it converges. If the p is less than or equal to 1, it diverges. Integral test also works both ways. Now, this one has a bigger or trickier application requirement. It says if it's a positive, continuous, and decreasing function on 1 to infinity. So it basically has to look like 1 over x. It's a smooth curve, stays above the axis, goes down all the time. Then 1 to infinity f of x, the integral converges, that means that the sum converges. If the integral diverges, that means that the sum diverges too. Then most recently we did the comparison test. You have to have two sequences that are both positive. You know about b sub n and you're interested in a sub n. And then if a sub n is smaller than b sub n and b sub n converges, that tells you a sub n converges. If a sub n is bigger than b sub n and b sub n diverges, then a sub n diverges. Now that doesn't cover all the possibilities. You can definitely have situations where you don't have a sub n less than b sub n and b sub n converging. You might have a sub n less than b sub n and b sub n diverging. So if you have a mismatch on those two conditions in the if this is true column, if they're mismatched, then it doesn't tell you anything. It would be inconclusive as well. And the limit comparison test is also nice. If you have both of the sequences greater than 0, you know about b sub n. Then if you take the limit of their ratio and it equals L, 0 less than L less than infinity, and one of them converges, then so does the other. Same thing, if one of them diverges, then so does the other. If that limit comes out to 0 or infinity though, or it does not exist, then the test is inconclusive. That's as far as we've gone on this list of tests so far.